Swayam Prabha. Digital India. Educated India.
Hi, good afternoon. Welcome to the course on comprehensive view of speech processing. So, today's lecture is 17th in series. So, today we are going to discuss about frequency domain analysis of speech. So, before going to the today's topic, prior to this, in the last one or two lectures we discussed about time domain analysis of speech. Basically, what are the various time domain features that are used for various speech tasks. Here you can see that here just listed out the four important features which can be extracted directly from a speech signal in time domain, and it will be useful for various speech tasks. Here these are the four time domain features that are extensively used in various speech tasks. So, they are like short term average energy, short term average zero crossing rate, short term autocorrelation function, and short time average magnitude difference function. So, these four features are very extensively used in speech processing for various tasks. So, we will just go through like one after another very briefly in 2-3 minutes, then we will move on to today's topic, that is frequency domain analysis of speech. So, in case of short term average energy, so this is used for basically for segmenting the speech into sound units. Like as we know that the speech is nothing but a sequence of sound units, and by using the short term average energy, so by analyzing the short term average energy contour, so one can able to segment the speech automatically based on the sound units that are present in the signal. So, basically here the sound units means with respect to the phonemes are like they are like either syllables or phonemes. So, that way you can able to split the speech signal into based on the sound units, that is phonemes and syllables, based on the finer variations in the short term average energy and all. And whereas by using a gross level of short term average energy, by using that one can able to segment the speech into voiced and unvoiced regions and all, because we know that in case of voiced region the speech signal strength is very high, and you can able to observe the periodicity, whereas in case of unvoiced speech regions the signal energy is very low. So, based on that one can able to identify that whether the given speech segment is a voiced segment or unvoiced segment. And here in this case actually the larger variations in the energy contour, based on that one can able to identify or detect the regions of voiced and unvoiced regions in a speech signal, whereas the finer variations in the energy contour are used to detect the speech boundaries with respect to the sound units that are present in the signal. And we can also detect the word and phrase boundaries or the silence detection from the speech signal using the short term average energy. So, here this is you can clearly observe, that means word and phrase boundaries or silence detection is nothing but in a speech we cannot speak continuously. So, when you are speaking, that means we will allow pauses or we will leave pauses at after certain words, or after a phrase we will allow certain pause, so that it will be intelligible and it will be for a perception purpose also the intended receiver or intended listener can able to properly understand the message. So, therefore, by analyzing the short term average energy, so where you can able to identify the boundaries of words and phrases, and in that process we can also identify that where the speech is present, where the speech is not present. It is nothing but silence detection. So, these things can be you can able to detect by using short term average energy contour. And also the begin end detection is nothing but when you are speaking usually will allow reasonable amount of pauses at the beginning of a sentence and at the end of the sentence also. So, by properly analyzing the short term average energy contour, we can detect the begin and end of the speech utterances or speech sentence. And finally, by knowing the pauses, the locations of the pauses and all, so one can able to multiplex the several conversations by exploiting the pause regions and all. It means that when you are speaking, it is not that all the time the person is speaking, like we will allow some pauses or will provide some gaps in between, and those gaps that does not contain any speech information. So, therefore, one can, if you can able to identify those pause regions, we can make use of them for effective utilization of the channel bandwidth by multiplexing with the other conversations. The next very important feature related to the time domain analysis of a speech will be short term average zero crossing rate, and this zero crossing rate provides you that like they approximate the spectral content or the spectral information that is present in the speech signal. It means actually if we want to find out the spectral details, we need to go in a frequency domain, or we need to like a transform by applying appropriate Fourier transform, we can able to get the details of the frequency domain information, and from that one can able to analyze the frequency domain content of a speech signal. But actually by applying a transform, and then that is a computationally intensive or computationally involved. So, if you want to analyze the frequency domain or frequency content of a speech signal without going into the frequency domain, that means from a time domain itself we can able to get some approximate information about the frequency content or the energy that is content in the different frequency bands can be observed by analyzing the zero crossing rate and all. So, we can able to obtain the zero crossing from the zero crossing rate, we can able to obtain the fundamental frequency that is present in the given narrow band signal and all. So, for that actually the requirement is that we need to have the speech signal should be a narrow band, then you can able to get whatever the frequency information that you can able to acquire from that will be more accurate and all. So, by using these expressions one can able to identify what is the dominant frequency which is carrying the energy in that narrow band can be observed by using these expressions, and for that you can see that here the ZCR can be computed. So, from the ZCR in the digital domain ZCR by 2 into Fs, that gives you the fundamental frequency associated to the speech segment and all. So, as we know that the ZCR correlates with the average frequency of a major energy concentration, because the speech signal is a wideband signal, because the frequency components that are ranging from low frequency to up to 4 kilohertz or higher. So, here if you compute the ZCR provides you like a frequency range or a frequency where the average, the dominant energy is focused or concentrated and all. So, therefore, by analyzing the ZCR of a speech segments, so if you can achieve the higher ZCR, it indicates that the energy is concentrated at a higher frequency, and if the ZCR is low, it indicates that the energy is concentrated at the low frequency regions and all. So, from that once if you analyze the ZCR for a speech segment, and with that we can able to decide whether the speech segment is voiced or unvoiced. In case of voiced speech segments, the ZCR is observed to be lower, and in case of unvoiced, the ZCR is observed to be higher. So, with this, but the computation of ZCR is very simple, like just if you can able to analyze the polarity of a speech signal, with that one can able to identify, one can able to compute the ZCR, zero crossing rate of a speech signal and all. So, but when you are detecting, when you are computing ZCR, that based on the sound unit, sometimes even though the speech sound that consists of voiced, because of the dominance of unvoiced part, you can able to observe the higher ZCR. So, then we can wrongly view that particular speech segment as unvoiced segment, but it is actually a voiced and a combination of both voiced and unvoiced, but the unvoiced component will be dominated. The same way, sometimes even unvoiced speech segment where the voicing is also present, where we can wrongly classify or view that as a voiced segment. So, and basically this, by knowing the ZCR, right, we can able to view this, can be useful, it can be used in the speech recognition purpose also. So, the idea here is that first the speech signal, since it is a wideband signal, so you can able to pass the speech signal through a set of filters which are the slightly narrow band signal. Like for example, you know that the speech frequencies are ranging from 0 to 4 kilohertz, right. So, if you pass this speech signal through a set of 16 filters or like 20 filters, where each filter bandwidth will be about 200 hertz or 300 hertz, then the output of these filters will be a bit of a kind of narrow band signals, and where if you can able to analyze the ZCR. So, with that we can able to analyze the frequency components that are present in the individual narrow band signals, where the dominant energy is concentrated and all. So, you can take the outcome of these ZCRs of all these filters, and that can be viewed as a feature vector, and you can use that feature vector for analyzing the or you can able to classify or discriminating the various sound units in the context of speech recognition. And here, even though we are computing ZCR in time domain, but that gives you the information related to the frequency domain. That means, in a particular frequency, what is the energy that is focused or concentrated. So, it means it is an indirect way of analyzing the spectral content in the time domain itself. And the next important feature that is used will be autocorrelation function, short time autocorrelation function, and we know that the short term autocorrelation function can be computed by using this expression, right. And so, this short term autocorrelation function provides you with that we can able to estimate the f naught. It means that the periodicity can be estimated or detected in a given speech segment, and this autocorrelation function can also be used in the linear prediction analysis, which we are going to discuss in the next lecture most probably. And so, once if you as we have seen that using autocorrelation function we can estimate the f naught. So, once if you estimate the f naught, so with which we can able to, it means using autocorrelation analysis we can able to detect whether the speech segment is a voiced or unvoiced, because in a given speech segment, if you can able to observe the periodicity in the autocorrelation function, means because we know that if a signal, if a particular segment is a periodic segment, and then if you compute autocorrelation function, the autocorrelation function is also observed to be periodic. So, that way one can able to estimate that given a speech segment whether it is a periodic segment or aperiodic. If it is a periodic segment, it means that it is a voiced segment, otherwise it is a unvoiced segment. So, that way by using autocorrelation measure, autocorrelation feature, one can able to decide or one can able to detect the speech segment as voiced or unvoiced. And but the computational complexity that is involved with the autocorrelation function is slightly higher, because if you see the formulation here, for computing one value of autocorrelation, autocorrelation value, right, r of k, for k varies from 0 to like given range. For every value of autocorrelation, here you can able to see that the number of computations that are required will be like almost like we need to perform n multiplications and all. We need to perform the n multiplications, and that means for every shift we need to have n multiplications to be carried out. And here we need to see that what is the range of these autocorrelation values to be computed in case of f naught estimation and in case of LP analysis. In case of f naught estimation, we need to perform autocorrelation coefficients has to be computed, minimum more than one period has to be done, right. Suppose for example, if a pitch period equals to 10 milliseconds and if the sampling rate that was done carried out will be 10 kilohertz, it means that like 10,000 samples per second, and if the pitch period equals to 10 milliseconds means there will be 100 samples. It means that you need to perform autocorrelation function for 100 shifts. Then only you can able to see some periodicity in the autocorrelation sequence. So, that way the computation of autocorrelation function is slightly bit expensive or computationally more expensive for estimation of pitch or for deciding whether the segment is voiced or unvoiced. We need to have more computation is involved in that. Whereas in case of LP analysis, we need not perform the autocorrelation function such a larger length. If you can able to perform in case of LP analysis, we know that the number of samples that will be considered in the history for predicting the present sample will be like we use that varies from 8 to 12 samples. So, therefore, we need to calculate the autocorrelation for 8 shifts, 8 to 12 shifts is good enough to compute the to perform the LP analysis or to derive the autocorrelation coefficients in case of LP analysis and all. So, now you can see that the other feature which performs similar to the autocorrelation function, but here the number of computations will be, or the computational complexity will be very less. Here you can see, here this is known to be like average magnitude difference function. So, what we are doing here is that instead of performing the multiplication between a signal and its shifted version, here we are performing a difference. We are computing a difference between signal and its shifted version. S of n is the signal and S of n minus k is the same signal shifted by k samples, and here instead of performing the multiplication unlike in the autocorrelation function, here we are computing the difference between these two, right, difference between these two. So, when you perform the difference between these two, so if the signal, suppose for example, the k equals to 0, it means the signal is not at all shifted. If you take a difference, it will get a 0. Then afterwards, when you shift the value of one of the signals, the same signal for different values of k, you will get the value will be like, the difference will be like more than 0 you will get, and again you will get somewhat minimum value when the shifted version is coincides or synchronized with the period, with the appropriately with the period of the signal and all. At that time you can able to find the minimum signal and all. So, that way when you compute a difference between the signal and the shifted version, if the signal is a periodic one, you can able to observe the valleys at a periodic locations and all. Whereas, in case of autocorrelation function, you can able to see the peaks in the autocorrelation function at a periodic locations, and the distance between the peaks indicates the pitch period. Whereas, here in case of average magnitude difference function, instead of peaks you can able to observe the valleys. So, the difference between or the distance between the two successive valleys gives you the pitch period of a given periodic signal and all. So, that way you can able to compute whatever the purpose of autocorrelation function in estimation of f naught, or in detecting whether it is a voiced segment or unvoiced segment, you can able to perform in a very less computational way or manner, you can able to do that. So, these are the 4 parameters, 4 important features that we can able to derive from the time domain analysis of a speech, which can be useful for almost all speech related tasks. So, the next thing today we will focus or we will discuss will be the frequency domain analysis of a speech. So, we already know that what is meant by frequency domain and what we can able to observe, and how to derive or how to observe the frequency domain information of a speech. So, for that we, in the previous lectures we discussed about the Fourier transform, right, and then the discrete Fourier transform and the fast Fourier transform. So, these transforms, by applying a Fourier transform on a speech signal, you can able to observe the frequency domain information present in the speech signal and all. And whereas here we will analyze the frequency domain analysis, or we can perform the frequency domain analysis using a filter bank, because these Fourier transform and the discrete Fourier transform, so they were derived, they were evolved in the 70s and 80s. Prior to that, if you want to analyze the frequency domain or frequency content of a speech signal, the way you can able to analyze will be using a filter bank analysis. It means that actually here the idea here is that in the filter bank analysis, so we know that a signal, suppose for example, if you want to analyze the speech or frequency domain content of a speech, so we know that the speech is a wideband signal, right. So, we know that the speech frequencies are ranging from 0 to 20 kilohertz, but out of that the most of the frequencies or most of the energy is focused at a lower range, that is up to 4 kilohertz or maximum up to 8 kilohertz. The entire energy will be, most of the energy will be concentrated in the frequencies up to 8 kilohertz. And if you want to conserve the bandwidth, if you want to analyze more preserve the bandwidth, that it means even up to 4 kilohertz analysis, up to by analyzing the frequencies up to 4 kilohertz is also reasonably good, where you can able to see that the most of the information or most of the speech content or the energies that is present in a speech signal is mostly concentrated 4 kilohertz or slightly less than 4 kilohertz itself. So, if you want to analyze the frequency the energies how it is distributed in that 4 kilohertz, for that purpose what we do is that, so these 4 kilohertz speech signal or 4 kilohertz is divided into different bands. Like for example, this 4 kilohertz, if you divide that into 8 bands, where each frequency band consists of range of like 500 hertz, like 0 to 500 hertz will be taken care by one of the filters, and 500 to 1000, then 1000 to 1500. Likewise, with the bandwidth of 500 hertz, if you can split the range of the frequency range from 0 to 4 kilohertz with the help of 8 filters, right, and if you pass the speech signal through these band of 8 filters, and now if you analyze or if you observe the outcome of each of this filter bank, each of this filter, right. So, if you here for example, assuming that here there are q filters, the q is 8 for example, assume that. So, in that case, if you analyze the outcome of this first filter bank, filter, so here the frequencies that you can able to observe will be 0 to 500, and here will be like 500 to 1000, and the third one will be like 1000 to 1500, and here the last one you can able to observe as 3500 to 4000, right. So, that way if you pass the speech signal through a set of filters, and if you analyze the energy content that is present in each outcome or each of this channel, and if you can if you derive if you can able to analyze or if you can able to concatenate these the energies of offered by various filters, like you can view this as a feature vector, and this feature vector represents the distribution of energy in different frequency bands, and this feature vector can be used for discriminating the sounds in case of speech recognition, and these feature vectors can be used to discriminate the speakers in the context of speaker verification or speaker identification, and this can be used for other applications such as emotion recognition or even the language identification tasks and so on. So, that way in earlier since as we do not have the facility to compute the frequency domain information through Fourier transform, right. So, that time people use the filters, they design the filters, set of filters, and pass the speech signal or wideband signal through these filters, where you can able to derive the narrowband equivalent of the speech signals through as the outcome of the filters. And if you analyze the energy content in each of this outcome of the filter, and the sequence of these energies are you can be viewed as a feature vector, and these feature vectors can be used for performing the different various speech tasks such as speech recognition, speaker recognition and so on. So, this is the basic idea about the filter bank analysis of a speech, with which by designing the set of filters and by analyzing the outcome, the energy associated to each of the output of these filters. So, with which you can able to get the idea about like how the energy is distributed across the frequency bands in the range of in the frequencies in the wide range of frequencies, and that can be useful for discriminating various sounds. And the way it will be performed will be, suppose for example, if you take a speech segment where it is like a voice speech segment, and as we know that here for performing the speech signal we need to perform like in a quasi stationary way, because as we have seen that the speech signal like it is a time varying signal, because when you are speaking here you can see that the speech signal is nothing but the production of the sequence of sound units in a continuum, right, and each sound unit has a different characteristics that we have observed in the acoustic phonetics, right. So, therefore, if you want to perform the frequency domain analysis, so it will be better to perform the frequency domain analysis on a shorter segments of speech. Otherwise, suppose if you want to analyze suppose 1 second or 2 seconds of a speech where it consists of multiple sounds, and if you try to analyze the frequency domain analysis or frequency content or the energy concentration in the various frequency ranges, so you do not get any meaningful information out of that, because that 1 second or 2 seconds of a speech consists of multiple sounds, and whatever the frequency domain information or whatever the frequency content or the energy distribution over the frequency content. So, that is related to a combination of all the sound units. So, you do not get any meaningful information related to that. So, therefore, if you want to analyze the frequency domain of a speech content of a speech signal, so you need to analyze on a shorter segments, where in this segment we are assuming that the speech characteristics are stationary. So, here we taken some 30 milliseconds or 40 milliseconds of a speech signal, and for that, if you by knowing the right now we can have this discrete Fourier transform tool. So, with that we can able to compute the spectrum. So, if you compute a spectrum by using a DFT, so you can able to see the spectrum will be something like that, because the spectrum is a discrete spectrum, and you can able to see the frequency content will be ranging from here to up to 4 kilohertz, and the energy will be distributed here. At low frequency content, the energy will be concentration will be higher, and as you move on at high frequencies, the energy that is present, the energy of the frequency components will be significantly low compared to the low frequency content. So, this is the spectral envelope of the given the voice or speech segment. And suppose if you want to perform this by using filter bank analysis, you can use a narrowband filters, a set of narrowband filters or set of wideband filters. So, the difference is that in case of narrowband filters, if you are using a narrowband filters, then you need to use a more number of filters to get the narrowband information, or like narrowband signals corresponds to the speech signal. So, you can see the narrowband means here you can see the peak, that means the bandwidth offered by each filter will be very small. So, therefore, you need to have more and more number of filters need to be employed to derive the spectral information of the given speech signal and all. So, by using these narrowband filters, and if you derive the spectral information, here how do you derive that one? Here you can see this is the set of narrowband filters. At each outcome of each narrowband filter, we will see that what is the energy that is associated. So, that way if you plot the energy values associated to each of this narrowband filter with respect to time, right, you can able to get this particular spectral envelope. You can able to see, since we are using a narrowband filters, so at the outcome you can also observe you can see the finer variations are known to be the pitch harmonics is also present in the spectral as a part of the spectral information content of a signal and all. Whereas in case of wideband, if you use a wideband filters, it means the filter bandwidths are very large, and you can see there is a lot of overlap that is present in a successive filters and all. So, therefore, if you analyze outcome of wideband filters, where you can able to see the spectral envelope, or you can say the spectral information for a given speech signal will be somewhat smoother, because here there is a lot of overlap between the successive filters. So, therefore, if you plot the energy values of these filters, then you can able to see somewhat the filter the spectral content, the spectral information or the spectral envelope is observed to be much smoother compared to the narrowband signal and all, compared to the narrowband filter bank. So, that way based on the requirement you can use either a narrowband filter or a wideband filter bank, so that we can able to analyze the frequency content that is present in the signal and all. Yeah, the same thing whatever I just mentioned here, the same like whatever the previous plot and this plot both are same, but here to provide more I just plotted the diagram slightly neat with you can say the narrowband filters. You can see that the filters bandwidth is very small and all, and the amount of overlap is also very less, whereas in case of wideband filters you can see that the filter bandwidth is larger and there is a lot of overlap. So, therefore, if you analyze the outcome of this narrowband filter bank versus the wideband filter bank, you can able to see that the outcome of wideband filter bank is observed to be much smoother compared to the narrowband filters and all, right. And here this filter bank analysis is basically used to analyze the frequency content present in the signal, and this filter bank analysis is initially used for the speech coding application, because in the 50s and 60s there at that time due to lack of computational power and not much proliferation of these digital machines and computers, at that time related to speech, the demanding application that was present at that time will be like the telephonic application, where the speech will be transmitted from one point to other point through a wired channels, wired and wireless channels and all. So, that time here the important, very important application or very demanding application related to speech will be like how do we represent the speech or how do we code the speech in a very effectively with less number of bits or with very less bandwidth and all. So, that the speech can be transmitted with a very minimum bandwidth, and so that at that time the channel bandwidth is very precision, very important. So, therefore, by if you can able to represent the speech in very compact way, so that the multiple channels can be multiplexed together in a given transmission cable itself. So, that way earlier in 50s and 60s the most of the research on a speech is on the speech coding, right. That means suppose in a telephonic application you are speaking through a telephone, and the speech signal whatever you are speaking, so that will be like it will be transmitted from a source to the destination through channels, and there at that time the channel bandwidth is very precious or very expensive and all. So, therefore, there at that time the most demanding research will be how do we can represent the speech in a very compact way, so that like multiple channels or multiple speech conversations can be put together and can be transmitted through a single channel and all. So, that was the most demanding application at that point of a time. So, here suppose for example, if we do not have any speech coding and if you directly transmit a speech signal, we know that the speech frequencies are like up to 8 kilohertz, the speech frequencies are present in a normal speech. So, therefore, if you want to like transmit the speech signal of 8 kilohertz, so we need to sample it twice that rate, that is 16 kilohertz transmission rate is required, slightly more than that is required. So, therefore, we will sample the speech signal at 20 kilohertz. It means that we need to send 20,000 samples per second, and again for representing a sample we need to have for accurate representation and all, we need to have more number of bits are required. Suppose if you assume that if you can represent each speech sample by 12 bits, right. So, therefore, the total the bit rate for transmission of a speech signal without any coding will be like 240 kbps. It means that per second we have 20,000 samples and each sample has to be encoded by 12 bits. So, therefore, 12 into 20 kilohertz 20,000. So, it gives you about 240 kilobits per second data rates are required for transmission of a speech signal and all through one channel, right. So, but is there a way to represent the speech or represent the speech in a very compact way? Instead of 240 kilobits per second, shall we represent or shall we code the speech such a way that in a very compact way less than 240 kilobits per second, right. So, that was the idea at that point of a time. So, for that we use the filter bank, right. So, it means here we have a speech signal and the speech signal will be passed through a set of filters here we have set of Q filters. Suppose assuming that if the number of filters equals to 16 for example, right, it can be 8 or 16 or like that is the way the number of filters used to be. So, assuming that if there are 16 filters, right, and each filter bandwidth will be like roughly about like 500 hertz. So, therefore, the 16 passband filters will put together will offer you a range of 0 to 8 kilohertz. It means that the speech signal whatever is there, so that will be passed through these 16 filters where each filter bandwidth equals to 500 hertz, right. So, therefore, all put together these will take care of the outcome of all these band pass filters, 16 band pass filters will split the speech signal into a narrow band signals. Earlier here the speech signal contains the frequencies from 0 to like 8 kilohertz or more than that, but here if you limit, if you are assuming that up to 8 kilohertz is reasonably good. So, therefore, by designing a set of 16 filters where each filter will offer a bandwidth of 500 hertz. So, that now if you look at the outcome of these filters like S1 of n, S2 of n and up to S16 of n, where S1 of n is a narrowband signal, narrowband speech signal where the frequency components will be 0 to 500 will be present over here, whereas S16 of n where it contains the frequency components will be like 7500 to 8000 hertz, right. So, that way each filter will be outcome will be limited in the frequency band. And now here we know that the outcome of each filter will be a narrowband signal. That means the actual frequencies are in the range of only 500, it is 0 to 500 here, and the next will be 500 to 1000, and next will be 1000 to 1500, and if you look at the last one, the frequency contents will be 7500 to 8000. It means if you look at the range, the bandwidth or the range of frequencies will be only 500, but here at this point, where at the beginning this filter bank will provide that range will be at a lower side, but here this range will be at a high frequency side. So, if you want to directly quote, if you want to directly sample the signal, so we need to here perform a sampling at a twice of this rate, like because here the maximum frequency equals to 8 kilohertz. So, therefore, we need to sample at 16 kilohertz, right. So, with that we do not get much benefit out of it. So, therefore, but here we know that the range of frequencies are less, that means here is a narrowband signal, that means the range of frequencies will be 500, the pass band is only 500 hertz, but this pass band is present at higher side here, whereas here the pass band is present at lower side. So, somehow if you can able to bring all these pass bands to lower side, all these because here the pass band is 7500 to 8000, and before that the pass band is 7000 to 7500, and here somewhere it will be 4000 to 4500, but the pass band is 500 only, that means the range of frequencies are 500 only. So, somehow if we can able to bring all these pass bands, right, to a lower side, then all the frequencies will become at a low frequency, then we can able to sample at a very lower rate, then we can able to achieve benefit, we can able to achieve lower data rates, representation of a speech in a lower bit rates. So, that was the idea in case of a speech coding by using a filter bank. So, here what we do is that, so these the pass bands whatever here, all these pass bands we need to shift towards the lower side, towards the lower low frequency side, because it is, even though it is a 7000 to 500, so but you will try to shift this to 0 to 500, and likewise here also suppose 5000 to 5500, so this will be, we will try to shift towards to 0 to 500. So, likewise all these pass bands will try to shift towards to 0 to 500. So, for that what we need to do is that we will pass these narrowband signals through a nonlinearity, some nonlinear circuits or nonlinear systems, where these nonlinear systems will try to shift these pass bands to lower frequency side or lower side or near to the 0 frequency, that will be done. And once if all these pass bands are bring to towards the lower side, then by passing these signals through low pass filters, where we can get all these pass bands at a lower side, then since all the pass bands are only 0 to 500 or whatever in the lower range, then we can able to sample again with lower rates, and with that we can able to get a desired lower bit rates can be obtained and all. So, this is the idea for using a filter bank analysis for a speech coding. So, we will see that what is this nonlinearity, how this nonlinearity will shift the frequency bands to lower side. So, that we will see in the next slide. So, here if you look at here, as we know that each of the outcome of a filter is a narrowband signal, like assuming that this is a narrowband signal offered by a filter, but here for the sake of analysis we consider this narrowband signal consists of only one frequency, is a sinusoidal, and this sinusoidal frequency is assuming that this is omega 1 is the frequency offered by this sinusoidal signal, right. And suppose for example, if you want to shift this omega 1 towards the lower side, still lower side or near to the 0, so what can be done, right. And so therefore, what we do is that we will pass this sinusoidal signals through, we apply a nonlinearity. So, here applying nonlinearity is nothing but just multiplying this time domain signal with this rectangular pulse train with the rectangular signal. So, if you look at this rectangular signal and if you multiply this signal with this, you will get a full rectified signal, because here the sinusoidal signal both it has a positive and negative signals, negative content, and now by multiplying this signal with this rectangular pulse train, you can able to convert this sinusoidal to fully rectified signal and all, like full wave rectification is obtained. And now this process, what we are doing in the time domain, we are performing the multiplication. We will see that what happens by applying a nonlinearity in a frequency domain. So, we know that this is the sinusoidal signal. So, therefore, the spectrum of this particular signal will be single frequency at omega 1, and this particular nonlinearity, that is rectangular wave, for this if you compute the Fourier transform, you can able to observe that the Fourier transform is nothing but whatever the periodicity was there. So, you can able to see the periodicity at odd harmonics, that is omega 1, 3 omega 1, 5 omega 1, and likewise up to infinity. All these harmonics are present, corresponds to this particular nonlinearity. And here what we are doing, we are performing a multiplication here in the time domain. So, therefore, whatever this full rectified signal, for this if you want to compute a spectrum, the spectrum of this signal is nothing but convolution of these two spectra, because here we are performing multiplication in time domain. So, the equivalent one in the frequency domain will be, if you want to compute the spectrum, or if you want to analyze the spectrum of this outcome of this nonlinearity will be like a convolution of these two spectra. So, this is the spectrum corresponds to this one, the signal, narrowband signal, and this is the spectrum corresponds to this rectangular waveform. And if you perform a convolution on this, you can see that at 0 shift you have the signal, and then if you shift one of the signal at the intervals of 2 omega 1, you can able to obtain you can able to get some like overlap and all. So, that way the last here, the last pane or the last waveform, last plot corresponds to the spectrum of the outcome of the nonlinearity and all. So, here if you observe here whatever the frequency content here, so the same thing is observed at a 0 frequency or at a very lower side and all. So, that way by applying for a narrowband signal, if you apply a nonlinearity, appropriate nonlinearity, then you can able to shift this frequency to a lower side, you can translate this frequency to a lower side. So, that way, as we have seen in earlier in the filter bank, each outcome of a filter bank will be very narrowband signal, right, and the narrowband signal is present at different frequencies. Suppose if the filter 16th filter, for example, if you observe, it is a narrowband signal, but the frequency range is around 7500 to 8000, and now if you apply a nonlinearity on that signal, then whatever the frequency content was there, so that particular frequency will be shifted towards the lower side. So, that way it becomes, the signal becomes like this, and now if you apply a low pass filter on this, then only this particular frequency content will be preserved, and the remaining all other the content will be removed, the frequency content will be removed. So, that way if you look at the previous slide, you can see that by applying a nonlinearity, you can able to shift the desired frequency content to lower side. Along with that, even other frequencies also present. So, to remove the other frequencies, we use the low pass filters. We use the low pass filter for every channel. So, then the outcome of a low pass filter will be contains very narrow band signal. It means the outcome of low pass filter will be contains only this part, and now here the signal is very narrow band, like that the frequency content will be a range of maybe 20 to 30 hertz, it may be there, only 20 to 30 hertz it may be there, and that too at a lower side. So, now for representing this 20 to 30 hertz at a lower side, so we need to sample at a rate of twice of that. Suppose if it is like, for example, we want to preserve up to 25 hertz, so it means that you need to sample at a rate of 50 hertz. So, therefore, each channel will be again sampled at a lower rate. That is what we are doing here. You can see that after you pass through a low pass filter, we know that here the range of frequency will be only 20 to 30 hertz. So, therefore, if you sample at a rate of 50 hertz, that is good enough for representation of this particular information. Likewise, here each channel will be sampled at a rate of 50 hertz, and there are 16 channels are there. So, therefore, for 1 second of a speech here, for every channel will give you the 50 samples and all, and there are about 16 channels are there total altogether. So, therefore, the output will be represented by in a 1 second we can able to represent say 50 samples per channel, and there are 16 channels are there. So, 50 into 16, that means there are 800 samples per second, 800 samples per second. And now, since the samples are highly correlated, instead of using 12 bits, by using amplitude compression and all, you can able to reduce the data rate, you can able to reduce the bits by, instead of 12 bits you can able to represent by either 5 bits or 6 bits or 7 bits, something like that. So, therefore, for example, here for 1 second of a speech, now we are representing with 16 channels, where each channel we are sampled at 50. That means each channel is represented by 50 samples per second. I have 16 channels are there. So, therefore, the total number of samples per second will be reduced to like 16 into 50, it becomes 800 samples, and now each sample is encoded by either 6 bits or 7 bits. Suppose if you code with the 6 bits, then we have 800 samples, each sample is represented by 6 bits. So, therefore, 800 into 6, that gives you 4800 bits. So, earlier we have seen that without this speech coding, right, earlier by using normal the PCM or digitization process, we need we have used we sampled at a rate of 20 kilohertz. It means that per second is represented by 20,000 samples per second, and each sample will be encoded by 12 bits. So, therefore, 12 bits or 15 bits, whatever, 12 bits for example, then the number of bits that are required for representation of 1 second of a speech will be like 20,000 multiplied by 12. So, that gives you about 240 kbps, 240 kb, that means 240 kilobits per second. Whereas, after when you perform the speech coding using this way, like by applying a nonlinear, by passing through filter bank, and again each pass band is passed through a nonlinearity, so that you can get all these frequencies will be shifted towards lower side, then by passing through low pass filter. And here my low pass filtered output contains the frequency range of only 20 to 30 hertz, then we can able to reduce the sample rate at a very lower rates of 50 hertz, right. So, therefore, now the number of samples that are required to represent the speech will be like each will be 50 samples per channel. There are 16 channels are there, 16 filtered outputs, and then 16 into 8, that gives you 800 samples. And now again these samples will be further by using appropriate amplitude compression and all, you can able to, instead of 12 bits, you can also represent with 6 bits or 7 bits and all. So, with that the total data rates can be reduced to 4800 bits per second instead of 240 kilobits per second, that is nothing but 240,000 bits per second, to you can reduce to 4800 or 5600 bits per second. So, it is a very great amount of reduction, almost like the order of like 40 times reduction in the bit rates for representation of a speech signal and all. So, that way at the sender side we will try to represent the speech at a very lower rates, and then this low bit rate speech signal will be transmitted through a telephonic channel. At the other end we will do the reverse, we will perform the reverse process and all, will perform. That means whatever the frequencies are there, so those frequencies will be again translated back to their original frequencies by knowing the frequency bands. Then afterwards whatever the amplitude compression, all of them will do in a other way, so that we can be able to get back the signal, speech signal will be get back without any distortion and all. So, that way this filter bank analysis is very extensively used initially for the purpose of speech coding in a telephonic application and all. So, this is the illustration of how the nonlinearity will be used to shift the frequencies to a lower side, and this is the practical case for speech signal. Suppose if you have a speech signal like, and if you pass the speech signal through a narrowband filter, where here the filter is like the center frequency is around 500 hertz and the bandwidth is about again another 500 or so. So, therefore, when you pass the speech signal through a narrowband filter, so the output of a narrowband filter, one of the filter banks, one of the filters of a filter bank outcome will be like this, right. And if you look at the corresponding spectra for a speech signal, normal speech signal, this is the spectrum, and this is the spectrum corresponds to narrowband speech signal passed through one of the filtered output. And now what we want is that whatever this one, so this has to be shifted towards lower side, this has to be shifted. So this is the case where the pass band is situated around 500 and all. The same way, if you take a filter at the other end to the extreme end, where you can able to see a similar characteristic at this end, at the high frequency end, right. And our goal is that all these the frequencies, all these the critical frequencies has to be shifted to lower side. For that, what we are doing, we applying non-linearity on this. That means whatever the signal, narrowband signal is there, we are multiplying this narrowband signal with a non-linearity, with a rectangular pulses, right. So with that, you can see that here you can see that the signal has both positive and negatives. Here you can able to see that the entire signal will be in a positive side. It is known to be the rectified signal and all. And now if you analyze the rectified signal, you can able to see that whatever the frequency band earlier it was there, it will be shifted towards 0, right. You can see that this is the spectrum of this non-linearity. And now if you perform a convolution between these two, you can able to observe that the outcome of this filtered this spectrum of this particular nonlinear output will be this way. It means that whatever here the information is there, so this will be shifted very close to the 0 and all. Now if you pass this through a low pass filter, so the low pass filter will preserve the low frequency content up to this part and the remaining part will be removed. And now this low pass filtered output will be you can able to encode or you can able to sample at a lower rates, because the frequency content is at a lower side at only up to 30 hertz. So therefore you can safely sample at a rate of either 50 samples per second or 60 samples per second. So that way for every channel will offer a very lower sampling rate, so that the bit rates can be reduced further and all. So this way we can able to use the filter bank analysis for the speech coding purpose. And now we will see that how the filter bank used for speech recognition, because as I mentioned that earlier, the only application that is extensively people have worked on or performed the research on a speech will be till 60s, even till 70s also, it is only the speech coding, because at that time the only application that was in demand, that is extensively used in the entire world, will be the telephonic application, where people used to speak or the speech signal has to be transmitted from one point to other point, right. And that time the channels are very expensive. So therefore whatever the speech representation, that has to be represented very compressed way or very compact way, so that you can able to perform multiplexing and you can able to carry out the this speech transmission very effectively. And now we will see that how this filter bank analysis later, since the filter bank analysis is used for speech coding initially, later we have the task of speech recognition. That means the machines has to recognize the speech is nothing but from a machine viewpoint, speech recognition is nothing but given a speech signal, it has to derive the equivalent text out of it. It is nothing but it has to decode or it has to find out the sequence of sounds that are present in the speech signal and all. So that was the task. So for that initially it was attempted by using the filter bank analysis, right. So for that people use the different types of filters. So the one that is used will be initially the uniform filter bank. We know that the speech frequencies are ranging from 0 to 20 kilohertz or whatever. So it is the entire frequency range is divided into uniform bands, like equal bandwidth. And now you can see that the first filter bandwidth is Fs by n. So likewise we will split the entire bandwidth of a speech signal into with equally spacing filters, right. And the center frequency of each band can be obtained by Fs by n into I, where I indicates the ith filter in a filter bank, right. And the number of filters will be q, and here the q will be varying, q will be less than or equals to n by 2. That means if q equals to n by 2, it means that if you look at here q equals to n by 2, if you put it, it means that the frequency range that we are considering will be up to Fs sampling frequency and all, right. And sometimes actually here we need not have the frequencies that need to be analyzed, need not be till the sampling frequency, because it is not for the perceptual purpose. This is for the purpose of speech recognition. It means that from the speech signal we need to derive the sound units. So, for that purpose we need not analyze the filters like till the sampling frequency and all, till the sampling frequency, because the sampling frequency we are doing with the Fs means the actual content of a speech or frequencies will be present only up to Fs by 2. So, therefore, the number of filters that are required will be Q will be always less than or equals to n by 2, always less than or equals to n by 2. Like Bi is nothing but Fs by n, and if the bandwidth is more than Fs by n, it means that the filters are overlapped. The filters whatever we are using, they are the overlapped filters and all. And if the bandwidth is less than Fs by n, then it is a problem. It means that the filters are not overlapped. It means that in the process we are missing some of the frequency information, frequency content in the speech signal and all, right. If the filters are overlapped means, it means that the entire frequency range will be taken care by all the filters together, because the filters are overlapped. If the filters are not overlapped means, between the filter, successive filter, if you are leaving some frequency content and those frequency content is not analyzed and not used for the analysis purpose, and later by missing that frequency content we may lose some information later on for the purpose of speech recognition and so on. So, therefore, as far as possible for a speech recognition purpose, so the bandwidths that will be offered by filters will be like a Bi should be greater than or equals to Fs by n. It means that the filters will be overlapped or required. If the filters are non-overlapped, then we are losing some information, right, the missing the speech details, spectral details. So, that is a loss of information that cannot be used for speech recognition purpose, right. So, later the next thing is the non-uniform filters. So, this will continue in the next class. So, we will stop here in this lecture. So, we will continue this one in the next. Thank you.